better than reading and gaining more and more knowledge. With these inspiring words said by the great physicist Stephen Hawking, I welcome the viewers in today's session. We are aware of the fact that electricity and magnetism are interconnected. Biot-Savart law gave the relation between the current and the magnetic field it produces. There is an alternative and appealing way in which the Biot-Savart law may be expressed. It is called Ampere-Circuital law. So, in today's program, we will understand Ampere-Circuital law and its application to find the magnetic field due to different magnetic systems. First, let's recall the work of the scientist Andre Ampere. Andre Ampere carried out a large number of experiments to explore the relationship between current electricity and magnetism, which culminated in 1827 with a publication. He hypothesized that all magnetic phenomena are due to circulating electric currents. Let's begin with the Ampere-Circuital law. Ampere-Circuital law considers an open surface with a boundary. The surface has current passing through it. Here in the diagram, C is the boundary of the open surface and current I is passing through it. We consider the boundary to be made up of number of small line elements. Let's consider one such element of length dl. Let Bt is the tangential component of the magnetic field at this point. This Bt is nothing but B cos theta. We will take the product of B cos theta and dl. Do you know that it can be written as a scalar product of B cos theta and dl, that is B dot dl. Yes, and on adding all the products or integrating it over the limit, we will have the sum of B dot dl. Also, the limits as the lengths of the elements get smaller and their number gets larger. Now we will state the Ampere-Circuital law. Ampere's law states that integral of B dot dl is equal to mu naught times the total current passing through the surface. Mathematically, it can be represented as integration of B dot dl equals to mu naught I. So, this is how we can state the Ampere-Circuital law and write its mathematical expression. This relation involves a sign convention given by right hand rule. Okay, let's understand how to use right hand rule. Curl the fingers of the right hand in the sense of a boundary and it is transversed in the loop integral B dot dl. Then the direction of the thumb gives the sense in which the current I is regarded as positive. For several applications, a much simplified version of Ampere-Circuital law proves sufficient. In such cases, we assume a loop called Amperian loop and it is chosen in such a way that at each point of the loop, B is tangential to the loop and is a non-zero constant B, or B is normal to the loop, or B vanishes. Any of these conditions should be there to choose an Amperian loop. We are going to apply this concept to find the magnetic field due to different magnetic systems. Let's discuss some cases and see how we can apply Ampere-Circuital law. Consider L be the length of the loop for which B is tangential. Length L and B is tangential. Then what will be the angle between B and L? Well, yes, it is 0 because both are tangential. IE is the current enclosed by the loop. IE is the current enclosed by the loop. Then on using Ampere-Circuital law, we get this is BL equals to mu naught IE. Moving to another case, taking a system with symmetry such as for a straight infinite current carrying wire. The boundary of the loop chosen is a circle, and the magnetic field is tangential to the circumference of the circle. And the integration of dl will be 2 pi r. So, the magnetic field at a distance r outside the wire is tangential and is given by b into length, which is 2 pi r equals to mu naught I. So, from here we have b equals to mu naught I divided by 2 pi r. Isn't it similar to the Gauss law of electrostatics, which is used to evaluate the electric field? So, yes, this is how the formula of Ampere's circuital law is used. There are some interesting points regarding the magnetic field due to an infinite current carrying wire. Firstly, the magnetic field at every point on a circle of radius r is same in magnitude. It means the magnetic field possesses a cylindrical symmetry. We all know that the field normally can depend on 3 coordinates, but in this case it depends only on one, that is r. Magnetic field lines form closed loops. This is unlike the electrostatic field lines, which originate from positive charges and end at negative charge. Also, it is the theoretical proof of Oersted experiment. Another interesting point to note is that even though the wire is infinite, the field due to it at a non-zero distance is not infinite. It tends to blow up only when we come very close to the wire. The field is directly proportional to the current and inversely proportional to the distance from the infinitely long current source. There exists a simple rule to determine the direction of the magnetic field due to a long wire. This rule is called right-hand rule, which we have discussed recently. It is important to know that Ampere's circuital law holds for steady currents which do not fluctuate with time. It also holds for closed loop, but yes, not for every case. Like it cannot be applied to the field at the center of the loop. In the next part of this program, we are going to calculate the magnetic field produced by 2 commonly used and very useful magnetic systems, that are the solenoid and the toroid. First, we will start by figuring out the magnetic field of the solenoid. Let's consider a long solenoid. Its length is large compared to its radius. It consists of a long insulated wire wound in the form of helix, where the neighboring turns are closely spaced. So, each turn can be regarded as circular loop. Look at the diagram on the screen. It displays the magnetic field lines for a finite solenoid. It shows a section of a solenoid in an enlarged manner. It is clear from the circular loops that the field between the 2 neighboring turns vanishes because they are in the opposite directions. Now look at this, it shows the entire finite solenoid with its magnetic field. Can you depict the magnetic field intensity at P and Q? Well, from the diagram we can see that the field at the interior midpoint P is uniform, strong and along the axis of the solenoid, whereas the field at the exterior midpoint Q is weak and moreover is along the axis of the solenoid with no perpendicular or normal component. Well, from the diagram we can see that the field at the interior midpoint P is uniform, strong and along the axis of the solenoid, whereas the field at the exterior point Q is weak and moreover is along the axis of the solenoid with no perpendicular or normal component. As the solenoid is made longer, it appears like a long cylindrical metal sheet. Let's see how we can represent it. This diagram represents the idealized picture. The field outside the solenoid approaches 0. That is why we will assume that the field outside is 0, whereas the field inside becomes everywhere parallel to the axis. Let's calculate the magnetic field due to this long solenoid. Consider a rectangular component, and this is Amperian loop A, B, C, D. Along CD, the field is 0 because it lies outside. Along transverse sections BC and AD, the magnetic field component is 0. That means there is no tangential component of the magnetic field. Thus, these two sections make no contribution. Let the field along AB be B vector, and the relevant length of the Amperian loop is L, and let's say this L is H, and N be the number of turns per unit length. That is, small n is equals to number of turns per unit length. The enclosed current IE will be the total number of loops into current in each section, in each loop. So, from Ampere's circuital law, we can write BL equals to mu naught IE. Here IE is the total current, which is written as BL equals to mu naught I. As we know that the Ampere's circuital law says that integration of B dot dl is equals to mu naught times I enclosed. Now, using this expression, we will find out the magnetic field due to the solenoid. Here ABCD is the Amperian loop, and it has components AB, BC, CD and DA. We will find out the magnetic field due to all the components one by one. For the CD, the magnetic field will be 0 because it lies outside the solenoid where magnetic field is 0. Now, considering the components BC and DA, since BC has the element DL like this, and the magnetic field here is in this direction. So, there is no tangential component along DL, and it is making 90-degree angle, and we all know that cos 90 is 0, and if cos 90 is 0, then integration of B dot dl will be 0, and there will be no magnetic field due to these components BC, and similarly for DA. Moving to AB. AB lies inside the solenoid. Let us say it is having length L. It means the integration of dl will be L, and I can write it as B taking outside. This is dl equals to mu naught. Now, the total charge enclosed will be given by n times the charge carrying in each loop. Next is B, integration of dl will be given as L equals to mu naught Ni, and I will write B equals to mu naught N taking L on the right hand side. This is N by L, and this N by L is nothing but small n, which is the number of turns per unit length. It means the magnetic field due to a solenoid can be written as B equals to mu naught N I. As we have already discussed, the direction of the field is given by right hand rule. The solenoid is commonly used to obtain a uniform magnetic field. Here we can see that B depends on mu naught, N and I. Will this B change if soft iron core inserted in the solenoid? Of course, as B depends on magnetic permeability of the medium. So, this is how we can calculate magnetic field due to a long solenoid using Ampere's circuital law. In the same way, we will figure out the magnetic field due to a toroid. If we bend a solenoid into a circular shape, it will look like this. This is a toroid. The toroid is a hollow circular ring on which a large number of turns of a wire are closely wound. Consider that it is carrying a current I. In order to calculate the magnetic field due to a toroid, we will use a sectional view of toroid. The direction of the magnetic field inside is clockwise as per the right hand thumb rule for circular loops. Here we can see the circular Amperian loop that are 1, 2 and 3, which are represented with the help of dashed lines. By symmetry, the magnetic field should be tangential to each of them and constant in magnitude for a given loop. It is quite clear from the diagram that the circular areas bounded by loop 2 and loop 3 is cutting the toroid, so that each turn of current carrying wire is cut once by loop 2. That means we will get the net current enclosed in this loop, whereas the loop 3 cut each turn of the wire twice. Here the incoming current cancels the effect of outgoing current. Here the net enclosed current becomes 0 in this case. Let's find out the magnetic field in each loop one by one. Starting from loop 1, let the magnetic field along the loop 1 be B1, and L is given by the circumference of the circle, which is 2 pi r1, because for loop 1 the radius is r1 and the current enclosed by this loop 1 is 0, because no current is flowing through it. And on substituting the value of L and enclosed current in Ampere's circuital law, what we will obtain? It will be B1 2 pi r1 equals to mu naught IE, which is 0. It means B1 is equals to 0. Thus, the magnetic field at any point P in the open space inside the toroid is 0. Moving forward, we will find the magnetic field at Q. Let the magnetic field along loop 3 be B3. Here L will be given by the circumference of the circle, which is having radius r3. As we have discussed earlier, that the current coming out of the plane is cancelled exactly by the current going into the plane. That is why the net enclosed current will be 0. It means B3 2 pi r3 equals to mu naught IE, which is 0. It means B3 is also 0. Thus, we can say that the magnetic field at any point P in the outside space will be 0. Now we are left with loop 2. Let the magnetic field along loop 2, that is inside the solenoid, is given by B, that is B2 is equals to B. We shall now consider the magnetic field at S, and here L is given by 2 pi r2, and let us say this r2 is equals to r, 2 pi r. Now the current enclosed IE will be given by IE is equals to NI. I is the current in each loop. Now using the Ampere's circuital law, we will get B multiplied by 2 pi r equals to mu naught Ni. Here B is equals to mu naught N divided by 2 pi r multiplied by I. and this n divided by 2 pi r is nothing but the number of turns per unit length, which is total number of turns n divided by 2 pi r. So, this expression can be written as B is equals to mu naught n I. So, this is the magnetic field due to a current carrying toroid. Isn't it the same expression that we have obtained in case of solenoid? Yes, it is. We have seen that the magnetic field in the open space P, that is inside, and the exterior point, that is Q point, is 0. The field B inside the toroid is constant in magnitude for the ideal toroid of closely wound turns. So, this is how we can use Ampere's circuital law to calculate the magnetic field due to a current carrying toroid. In reality, the turns of the toroidal coil form a helix, and there is always a small magnetic field external to the toroid. It is being ignored theoretically. Since then, we have learned that there exists a magnetic field due to a conductor carrying current which obeys the Biot-Savart law. Further, we have learned that an external magnetic field will exert a force on a current carrying conductor. This follows from the Lorentz force formula. Now, can you think what will happen to the two current carrying conductors placed near each other? If we connect the understanding of Biot-Savart law and Lorentz force, we may conclude that these two closely placed conductors will exert magnetic forces on each other. In the period 1820 to 25, Ampere studied the nature of this magnetic force and its dependence on the magnitude of the current, on the shape and size of the conductors, as well as the distances between the conductors, and it is something remarkable. Now, we shall take the simple example of two parallel current carrying conductors. As we can see in the diagram, there are two long parallel conductors A and B separated by a distance d and carrying parallel currents IA and IB respectively. The conductor A produces the same magnetic field BA at all the points along the conductor B. Which rule will be used to find the direction of the magnetic field due to this straight current carrying conductor? Well, yes, the right hand rule tells us that the direction of this field. Okay, let's see how we can find it. Now we will find out the direction of the force experienced by each conductor. Here, as we can see, that IA is in this direction. Now, from the right hand rule, what we can say is, if this thumb is representing the direction of the current, these curled fingers will give you the direction of the magnetic field. And due to this conductor A, the magnetic field is going like this, and for this B, it will be into the plane, which is represented as cross. Then this current is IB, which is in the upward direction. Now, using right hand rule, what we will do is, we will align our fingers along the direction of BA and the thumb will be in the direction of the current. So, what we can see is that the direction of the force is perpendicular to this plane. This is FBA. Similarly, we can find out the direction of force on conductor A due to conductor B. So, what we will do is, again we will use right hand thumb rule, and on applying this, what we can see is, if this thumb is in the upward direction and the magnetic field due to this B will be outward on this conductor A, and I am representing it like this. This is BB, which is why BB? Because it is experiencing the magnetic field due to this. Now, this is out of the plane. Now, again use right hand rule, and this IA is in the upward direction and this magnetic field is out of the page. So, what you can see is, the direction of the force will be perpendicular to this plane, and which is this FAB, which is giving you the force experienced by A due to B. So, this is the direction of force AB and this is the direction of FBA. It means they are attracting each other. And if I reverse the direction of the current of any of the conductor, they will be in the opposite direction. It means they will repel. So, we can state that parallel currents attract and anti-parallel currents repel. Now, we will figure out the magnitude of the force on both the conductors. Using Ampere's circuital law, we have the expression of magnetic field produced by the conductor A. So, we have find out that BA is equals to mu naught IA divided by 2 pi D. D is the distance between the conductors. Here we are going to find out the force on a segment L of B due to A. So, I will write force on B due to A and we know the formula, it is ILB. Here I will be of the current flowing in the conductor B, L is the length of the conductor and B here will be taken of the magnetic field due to conductor A. So, I can write FBA equals to IB L. Now, substituting the expression of BA here, we will get mu naught IA divided by 2 pi D. So, from here we can say FBA is equals to mu naught IA IB L divided by 2 pi D. So, this is the force on conductor B due to A. It is of course possible to compute the force on A due to B. From considerations similar to the previous case, we can find the force FAB on a segment of length L of A due to the current in B. It is equal in magnitude to FBA and is directed towards B, like F is equals to AB. And here I will write it as FBA is equals to minus of FAB because they are in opposite directions but equal in magnitude. It is quite interesting to note that this is consistent with Newton's third law. Thus, at least for parallel conductors and steady currents, we have shown that Biot-Savart law and the Lorentz force yield results in accordance with Newton's third law. Now, using the expression of FBA, we will try to define SI unit of the current, that is ampere. Let FBA, that is small FBA, represent the magnitude of the force FBA per unit length. It means we are taking FBA equals to FBA divided by length. As we have already derived that FBA, that is force on B due to A, is given by mu naught IA IB L divided by 2 pi D, and I can take this small n on the left hand side, then I will get mu naught IA IB divided by 2 pi D. It means FBA is equals to mu naught IA IB divided by 2 pi D. Here FBA is force per unit length. When D is equals to 1 meter, and on substituting the value of mu naught and taking current through the conductors as 1 ampere, that is IA equals to IB equals to 1 ampere, I will get force on B due to A per unit length equals to mu naught. This mu naught is 4 pi multiplied by 10 raised to the power minus 7 multiplied by 1 ampere 1 ampere divided by 2 pi 1 meter. D is equals to 1 meter. So, on solving it, I will get force on B due to a per unit length equals to 2 multiplied by 10 raised to the power minus 7 Newton per meter. This is the magnitude of FBA. The ampere is the value of that steady current which, when maintained in each of the two very long, straight, parallel conductors of negligible cross section and placed 1 meter apart in vacuum, would produce on each of these conductors a force equal to 2 multiplied by 10 raised to the power minus 7 newtons per meter of length. This definition of the ampere was adopted in 1946. It is theoretical definition. In practice, one must eliminate the effect of Earth's magnetic field and substitute very long wires by multi-turn coils of appropriate geometries. An instrument called the current balance is used to measure this mechanical force. Try to explore the working of this instrument. We may even define the SI unit of electric charge as when a steady current of 1 ampere is set up in a conductor, the quantity of charge that flows through its cross section in 1 second is 1 coulomb. So, in today's session, we have learnt ampere circuit law with its application and force between two current carrying conductors and defined 1 ampere. Now, we have understanding of magnetic field and force due to different magnetic systems. It is quite an interesting phenomena occur in the presence of two solenoids. Try to study about this. So, keep exploring till we meet again.